What's up, world? It's Math Nathan here. I got something cool I've been working on I want to share with you guys, right? So the way we start this off is let's start with a thought experiment. So let's say we have an arbitrary island out in the middle of nowhere, and on this island we have two populations, a population of predators and preys. The prey are going to be some happy-go-lucky beach bums, and the predators are going to be some carnivorous man-eating koalas, alright? So the beach bums eat coconuts. There's a magical coconut tree, never runs out of coconuts. So the beach bums can eat and procreate and live happily. The koala bears only eat the beach bums. There's no other food supply on the island. So the koala bears start dying as the number of beach bums decrease because they have less food, right? So they're intimately related. So there's a lot of interesting questions you want to ask about this. Can the population come to some sort of stability point, right? Can the koala bears and the beach bums live together in harmony some way? And there's actually a lot of ways we can figure this out. What you have to do is you have to go ahead and model it. And you can set up a system of dynamic equations, differential equations, relating the populations between each other, and explore it and do a lot of stuff with math. So if you look here on my post, I wrote a post about this. It's pretty in-depth if you wanted to go and check out the mathematics and deriving everything. So we've got two equations here. The first equation represents the rate with which the beach bums population is changing over time. It's the first derivative. The only way a population is going to change on an island, since they can never leave, is if either they're born or they die. And, it makes good sense. So the rate with which the population is changing is equal to the rate with which they're born minus the rate with which they die. Right? And the koala bear population is a little different. Right? The way that they're born, the way that they're born is dependent on the number of beach bums there are, because that's their food, and the rate with which they're dying is proportional to the number of beach bums that are dying, because then they'll have less food to eat and they'll start dying themselves. So this is our dynamic system right here. Now what we have to do next is solve it. What you're going to get is you're going to get two analytic equations, and each one is going to give you the population of either the beach bums or koala over time. It's going to tell you exactly the number of beach bums or koalas there are given two initial conditions. So once you know what the solutions are, you can go ahead and take a look at what the stability points might be. And these stability points are going to be where neither population is changing. Their populations are staying pretty stable. So there's two, there turns out to be two of them. The first one's pretty intuitive and makes good sense, and that is if there are 0 koala bears and there's 0 beach bums, because they're all dead and no one's being born or dying. So it's not very interesting, right? That one's rather intuitive. And this right here is a graph of the phase plane. This is the stability point 0, 0 here, and it's showing the population trend over time. And there's another stability point. It just so happened, it turns out to be dependent on some of the coefficients in the Lotka-Volterra equation. If you want to find out what those are, you can check the post out and check those. And here's the other stability point right here. This is a neutrally stable center point. So the populations stay pretty close to this one. So what I did after taking a look at a lot of this stuff was trying to understand wholesomely what this means. Is I visualized the data, because I figure once you're able to visualize data and you're able to see what it means in real life and its applications, it's just a lot more intuitive to people. So I wrote a program to visualize it, so we can take a look at what this means. Let's see how it works, right? So this right here is going to be the phase plane. The x-axis is the beach bum population, and the y-axis is the man-eating koala population. That's what a phase plane is, right? Now the vector field inside is showing you the relationship of the solutions over time. It's showing the tendency with which they change over time at any given point. So the solutions are going to follow the arrows in the vector field. This other graph I have here is population versus time. It's pretty intuitive. You've got the y-axis is the population, x-axis is time, and the red solution is going to be the number of koala bears, and the blue solution is going to be the number of beach bums. So I can just click anywhere on here arbitrarily, and we're going to find the solution as it oscillates around, and we're going to see what the populations are over time to give us a really good understanding of what a phase plane is. So let's say I choose 4,000 beach bums and 3,000 koala bears, right? This is our starting population. What's going to happen? Well, we click right here. So we can see the population trend over time, and we can see the number of populations as they change over time as well. So what does this mean? I mean, this makes a lot of sense. So if the red line is the number of koalas, so let's say there's very few koalas right down here, right? Look at the beach bums. Their population is huge. So the few koalas that are here, they have all these beach bums to eat, so they just start gobbling them up, and they start getting their population grows tremendously. But they ate so many beach bums, their population declines over time. And now the koala bears are at a maximum here because all the beach bums are dead, so they start dying as well. And so the beach bums start dying over time, and then the population of the koala bear, the population of the beach bum starts increasing again because there's less koala bears eating them. And so that's exactly what this solution is doing over time, and we can see that right here. So we've got the neutrally stable center point here. We can see the behavior of some populations that are a little bit closer. There's less oscillations. The magnitude, the change in the populations, the magnitude's a little smaller. And we've got this neutrally stable, or this unstable center point here. So what does that mean? That means if we get populations really close to it, say these, they're not going to remain stable. They're going to get way out of there. So if there's hardly any koala bears, then these beach bums are going to be able to just proliferate like mad. You know, they eat coconuts and they get real frisky, and they make lots and lots of beach bums. And the koala bears eat a whole lot. They have huge magnitudes here. So this is a really good way in my mind to visualize exactly what's going on, to see how you can relate the two of these together. You know, the closer you get to the middle here, you get closer to the stable point, the fluctuations are getting really, really small. And I guess it'd be interesting, a curious question is, what actually happens if you get right here in the middle? What's going on here? And there's plenty of theories about it. I guess what's actually going on is every single time a beach bum is born, there's a koala bear sitting there in the hospital room waiting for him to be born. As soon as he's born, he just gobbles up the baby, and then he kills himself, right? So that's the only way that the populations could stay completely stable. For every single time a beach bum is born, the koala bear dies. I find visualizing your data to be really intuitive. It just makes a lot more sense, being able to understand, you know, what it actually means in the real world. You know, you see this phase plane, you don't know what it means, but you've got this population versus time graph here to like really set it in stone and really give a good foothold of what it meant. So I hope this was as profound for you guys as it was for me when I made it. I learned a lot about it. If you guys have any questions about the code, you can get it at my GitHub repository if you want, if you guys want to go ahead and play around with this program. If you have any questions on it, feel free to email me, ask me any questions you want. And I hope you guys enjoyed the post. I hope you learned a lot about this stuff. And I also want to give a quick shout out to my boy Ian Johnson for helping me out with the program and everything. So I guess I'll hopefully be seeing you guys a little later on some more of my posts.